Okay, so for example 4, if we remember, we had this beam. It had a flange here of 1,100 millimeter. This thickness here, HF, was 100. This was given, D was 600. Here we had 830 Ms. And we had calculated that's 5,600 millimeters squared. We also had calculated AS reference. And we found that since AS is larger than AS reference, we have T-beam analysis. Okay, so when you do this concrete design handbook method, there's two situations. Okay, the first situation is if A is smaller than HF, right? If A is smaller than HF, this neutral axis depth is going to fall within the flange like this, right? In that case, we saw it's like you're analyzing a very wide rectangular beam like this, because the compression zone is what's important for the concrete, right? Below the neutral axis, we said whatever's in the concrete is not so important. So in that case, you would analyze this just using table 2.1 like we saw before. But in this example here, we found that since AS is larger than AS reference, right? Since AS is larger than AS reference, we have this situation. So in this case, the neutral axis is going into the web here, and this is the area of compressed concrete like this. So in this case, we have to do T-beam analysis. Okay, and that's what we need to do here. So in this first case, when A is smaller than HF, you just use table 2.1 as usual, and there's nothing that's new. When you're in this second case, when AS is larger than AS reference, A is larger than HF, then you need to use this procedure I'm going to show you now, where you need to use the combination of table 2.3 and table 2.1. Okay, and when we do this moment resistance, you're going to see we're going to split it up into two parts. One part that comes from the flange, and another part that's going to come from the web. Okay, and we have these two equations that we're going to apply for the flange part and for the web part. So this part here, this is for the flange. And this part here, over here, is for the web. Okay, so the way this works is the total steel that we have here, right? The total AS is 830 M, which we had found is 5,600 millimeters squared. What we're going to do now is we're going to split it into two parts. A first part, which we're going to call ASF, okay? And that's going to be the one that goes into the flange. And a second part, which we're going to call ASW, which goes into the web, okay? So we'll see now when we apply this example, we're going to see these two things. Okay, so what's the first thing to do is we have to figure out what this ASF is, because if we know it, then we can split that steel into these two portions. Okay, so to do this, we have to go into this table 2.3, which is the new table that we're going to use, and we're going to determine rho F based on D over HF. Okay, so let's calculate D over HF. In this example, it's 600 for D, and HF is the flange thickness, that's 100. So we get a number which is 6.0. And in this example, we also have F prime C, if you remember, it's F prime C of 25 MPa. With these two things, we can go to table 2.3, and we'll find a rho F, which I'm going to show you now. It's equal to 0.65%. Okay, so let's go to this table 2.3. Looks like this. Okay, so it has a T-beam here figure over here. You go to F prime C, we have 25 MPa. And we found that this D over HF is 6. So with that, we can find this rho F of 0.65%. Everybody followed what I did? Okay, so that's how you get this rho F. It's 0.65%. It's from table 2.3. The two inputs are D over HF and F prime C. Okay, once I know this, I can determine ASF. We know rho F is just equal to this here. So then we can isolate for ASF. So ASF is equal to rho F times BF minus BW times D. I'm just rearranging this equation here. So we have 0.65% times BF, it's 1,100 minus BW, which is 300 in this example, times D, which is 600. So if I do this, I'll find 3,120 millimeters squared, right? So this is this ASF. Okay, we found is 3,120 millimeters squared. Okay, now I can get this ASW. I know the total is 5,600. So what's left over? It's the difference between the two. So for ASW is just equal to AS, which is 5,600 minus ASF, which is 3,120. So that gives me 2,480 millimeters squared. So that's this ASW right here is 2,480 millimeters squared. Okay. Once we do this, we're going to determine the KR for each of these. So we're going to determine the KR for this 3,120 millimeters squared, and we're going to determine the KR for this 2,480 millimeters squared. Okay, so this one here, we know the rho that's associated with this. It's 0.65%, right? That's what we use to get ASF. And for this one, for the rho W, is just ASW over BWD. So that's 2,480 divided by 300 times 600. So this gives me 1.38%. That's rho W. Okay. So now in this next step, as I said, we're going to use both of these rho values, and we're going to go to our usual table. So we go to table 2.1. So here you're going to see I'm going to use table 2.1. Same thing here. I'm going to use table 2.1. Okay. Except here, I'm going to take rho F. So rho F is 0.65%. And here, I'm going to use the rho W. So here, I'll use rho W. So rho W is 1.38%. And here, I'm going to end up solving for something I'm going to call MRF. And here, I'm going to solve for something that I call MRW. Okay, and in both cases, I'm going to use this table 2.1. So let's start with the first one to solve for MRF. So we know rho F is 0.65%. And we know F prime C is 25 MPa. So if I go into this table 2.1, I go to table 2.1. So that's the usual table we're using. And I look into here, we have 25 MPa concrete. We have rho F, which is equal to 0.65%. So that's somewhere in between these two here. That's the rho F. So it gives me a KR, which is in between these two. If I do interpolation, I'm going to find the KR, which is 2.025 MPa. Okay. So here, when I go into this table 2.1, I feed in these two things. By interpolation, I'll find this KRF, which is equal to 2.025 MPa. Okay, this is from table 2.1. Okay, the same thing. I'll go to this table 2.1, but now I'll use rho W. So here I'm going to take rho W, and I'm going to take the same F prime C of 25 MPa, and I'm going to solve for KRW. I'm going to call it. And again, it's from table 2.1. So if I look up this 1.38% and 25 MPa, I should find, let's look at that. So now we have, we still have F prime C of 25, but we have rho of 1.38. So we have to keep going. until we get to 1.38. So it's in between these two here. Right? It's in between these two. So KR is going to be in between this. So it's 3.85 if I do interpolation. So here I'll find it's equal to 3.85 MPa. Okay. Once I know this, I can determine each of these KR values, these MR values. So MRF, again, this is for the flange. Right? So here, just to be clear, this one I'm using to get MRF. And this one here, I am using to get MRW. And if I add those two, I'll get the total MR. Okay, so for MRF, this is the equation that we're going to use. So it's just KRF that we just found, 2.025. But I be careful here. I multiply by BF minus BW times D squared. Okay, because here, if I look at this part, basically what I'm doing, here's my T-beam. Okay, it looks like this. What I'm doing is I'm taking this part of the flange. Okay, so that's why it's BF minus BW, right? This whole thing is BF. And this thing is BW. And then here I have this amount of steel, which I called ASF. So if I take the force couple from this part of the concrete and this ASF, I'll end up with this MRF. So that's why I multiply by BF minus BW times D squared. Okay, so I have here 1,100 minus BW 300 times D squared, which is 600 squared, all this times 10 to the minus 6. Okay, if I do this calculation, what do I end up with? I should end up with 583 kilonewton meter. Okay, so that's the first part of the moment, this MRF that we're getting here. Okay, then I can get this MRW. The MRW is the same idea, but I'm taking here this T-beam here, and I take the web portion. So I'm taking the web portion over here, and this here, this is ASW. Okay, so here I'm taking the web portion, and I'll use this equation. So I had found this KRW, it's 3.85 times BW, which is 300, times D squared, which is 600 squared, times 10 to the minus 6. This gives me an MRW of 416 kilonewton meter, right? So our total MR is just equal to MRF plus this MRW, right? So plus 416, and here we had 583. So if I add these two up, I'll end up with the total MR, which is equal to how much here? I will get 999 kilonewton meter. Abdullah, sorry, could you explain what you wrote there on the top left corner in regards to MRF and MRW? This? Okay, like I said, okay, here we have to go back to the theory. We said to calculate this moment resistance, we're basically doing this. We're taking our T-beam and we're splitting it into two parts. One part where we have this flange portion with this amount of steel ASF, and the second part where we have this web portion with this amount of steel, which we called ASW. Okay, so in this method, when we're using this concrete design handbook table, we start with the total amount of steel and we split it into two parts. The first part, ASF, which is going to be for the flange, and ASW, which is going to be for the web. Okay, and this ASF part, I use it to get MRF. And this ASW part, I use it to get MRW. Not sure if that explains what I meant. There was another question. So KRF and KRW are from the same table. Catalina is asking this. Yes, that's correct. You get both of those from table 2.1. Okay, where did I use the table 2.3 is just to get this, right? I have this total amount of steel, and I have to split it into this ASF, ASW. We only use this table 2.3 to know what this ASF is, right? Once I know this, then for the rest of the problem, I just use table 2.1. Okay. So hopefully that's clear. Can you show how to use table 2.3 again? Yes. Okay, so it's right here at this step, right? So that's the first thing I do. I have this total amount of steel. I have to split it into two parts, ASF, ASW. So I use this table 2.3 to determine this ASF. Okay, so what do I need in this table 2.3? I need this D over HF. So that's the first thing I calculated. So D is 600. That's this depth here. HF is this thickness here, 100. So I take this ratio, I get 6.0. And then I have F prime C, which is 25 MPa. So I go into table 2.3. Okay, I have 25 MPa concrete. I have D over HF, which is equal to 6. Okay, so with that, I can come in here, and this is the rho F, 0.65%. Okay, so I start with this, then I go to this, and then I will get my rho F. Okay, once I know rho F, then I can determine ASF using this formula here that I had. Hopefully that's clear. All right, good. Okay, so there is a tutorial, as I said, tutorial 4. It does another example on this. And hopefully after that, and after you see this example again, the video is also recorded. You can hopefully understand how to do it. You basically need to go through this once, and then it's very easy. Okay, so that's this example. And if you compare this 999 kilonewton meter, we had done it by hand, and we had found 994, right? So this is just because of rounding and some other things. They're slightly different, but you can see they're very similar. Okay, so let's continue on here. So hopefully everybody's done here on this page. Okay, so this is just learning from these examples. We said that in a real floor system, you have a choice of analyzing these beams as rectangular or T-beam, but we just saw the T-beam. It's good, but it takes more time, right, than the rectangular analysis. So it would be good to know when to use which one, right? When to just ignore this T-beam part, and when is it useful to do it. Okay, so if you look at this example that we just did, this one here, it was heavily reinforced. It had 830 Ms. If you analyze this as just as a rectangular, ignoring these flanges, you would find, in fact, it would be over-reinforced. Okay, so you can go through the calculations here, but you would find it would be over-reinforced. And this moment here, this moment resistance, again, I haven't done it. Just correct this because I think there's a mistake. This moment resistance would be 678 kilonewton meter. Okay, for this 830 M beam here. If I ignored these flanges and I just analyzed it like a rectangular, I would find it 678 kilonewton meter. If I took the T beam, we just found it's around 994 or 999 kilonewton meter, just like we did. So in this case, it makes sense to account for these flanges and do the detailed T beam analysis if I have this beam as part of this floor. Okay, so if you look at these two examples that we looked at in this problem set, the first one, we had 320 Ms. That was a lightly reinforced beam. In that case, we saw when we did the rectangular beam and then we did the T-beam, we saw there's very little difference, right? 186 versus 195. You still get a little bit more efficient moment resistance with the T-beam, but the two numbers are similar. Whereas if the beam is heavily reinforced, now it makes more of a difference. Again, this is 678. You can see the numbers are quite different here. Okay, so these are just some rules of thumb you can remember. Comments: there's limited difference when comparing the results of the rectangular versus T-beam if you have a lightly reinforced beam like this one where you had 320 Ms. Okay. However, there's a significant difference in the order of 30% when comparing the results of the more heavily reinforced beam in the second example, this one here. Okay, so we can conclude for lightly reinforced beams, there will be no significant difference in the moment resistance obtained using rectangular versus T-beam analysis. However, once you start to get a heavily reinforced beam, then you would get much larger moment resistance when you account for these flanges. Okay, so this is more like a practical design point, because we said these beams, they're going to be most of the times as part of these floors. So you want to choose, do I ignore these flanges or I consider them? Then that's a practical point for you. Okay, for this course, I will give you this shape, right? So if it's a T-beam shape, you need to analyze as a T-beam. All right, so let's look here. There's another thing I didn't cover yet. So let's go back to our handout and let's continue here. So now we're in lecture 4.1, T-beams in the theory, and we're going to continue. So we just did this concrete design handbook. And I want you to go, let's skip this one here. Go to page 11. We're going to go through these design requirements for T-beams. Okay, so in fact, the design requirements for T-beams are exactly the same as rectangular beams, except there's like one extra clause, but I've put everything again for you so we remember. So the CSA flexural design provisions that are required for rectangular beams with tension-only steel apply to T-beams as well. However, there's additional requirements which are specific to T-beams, and these are given in this clause, clause 10.3. Okay, so these we saw before. There's the maximum amount of tension reinforcement. The way you would do that is you do this CD check like we did in the previous two examples. We didn't do it in the CDH example, but we did it in the hand calculation. So that would be your check for your ensuring that you don't exceed the maximum amount of reinforcement. And then there's the ductility requirements we mentioned is just 0.8 of this thing here. Okay. Then we have the minimum amount of reinforcement. This also applies for T-beams. The only thing you need to be careful is this BT. This BT is the width of the tension face. So if you have a T-beam which looks like this and it's under positive moment, we said the compression is going to be at the top, tensions at the bottom. So this BT we said is the width of the tension zone. So what would you use in this equation here? You would use BT equals to BW, right? So if you have a T-beam and you want to do this AS min check, you need to put in here BT, which is this width BW. But let's say you have a situation where you have negative moment. Okay, so you have negative moment now. Okay, so let's say you have a cantilever beam like this, and you still built it as a T-beam. It has a T-beam shape like this. So if you took a section in here, you have a T-beam shape. Okay, and it's under this distributed load like this. Okay, in this case, we'd have a negative moment like that, right? M negative. So in that case, as opposed to this case, right? If you have a simply supported beam like this, same idea. This is a T-beam. In this first case, compressions at the top, tensions at the bottom. So here, therefore, BT equals to BW, right? In this equation, you would use BT equals to BW. Whereas in this second case, we have a cantilever beam. Where's your tension? Is it at the top or at the bottom? Where's the tension for this cantilever case? Where would the tension be? At the bottom or at the top? It would be at the top, right? You would place your steel in here, right? Whereas here, your steel is down here. So tension's at the top, compression's at the bottom. So in this case, you would take BT is the width of the tension zone. So what would it be equal to? It would be equal to BF, right? In this second case, where you have negative moment, you need to be careful. You take BT equals to BF because this is where the tension is. Whereas in this first case, your tension is at the bottom. So you take BT equals to BW. Everybody got this? This is a fine point. You need to be aware of the moment when you apply this AS min equation, because this is the width of the tension zone. All right, so that's one point you need to be careful of when you're doing T-beam analysis. When you do this AS min check, you have to be careful. Okay, There's other requirements which are the same. You have the minimum cover requirement. You have the minimum bar spacing. Just correct this here. It's 1.4 AG here, like we saw before. So that's exactly the same. Okay, and then you have this 30 millimeter, and then you also have the Z factor requirement, the skin force reinforcement, and deflection checks. All that would be the same as rectangular beams. Okay. Hopefully everybody's done here. Okay, so then there are specific requirements for T-beams. Okay, one of them is how do you determine this effective flange width? Okay, how do you determine this effective flange width? Up to now, in the problems I gave you BF. Okay, so if it's just a T-beam, right? We've just built this beam in the shape of a T. Then you don't need to do a calculation, right? Here, it's easy. You just determine BF. But let's say this T-beam is part of a floor system like this, right? In that case, you need to figure out what is this BF here. Okay, so there's a clause that discusses this here, 10.33 and 10.34. It gives you an equation that you use to determine BF. Everybody got it? So if it's a T shape, it's a beam on its own, then you just take BF based on the dimensions. But if it's part of a floor system like this, you need to figure out what's this BF, okay? So this BF is gonna depend on the type of loading, the structural system. Is it a simply supported beam or is it a continuous beam, right? This affects it. What's the spacing between the beams? So what's this spacing here, right? What is that spacing? And the relative stiffness of the slabs and the beams. Okay, so there's a table here which explains this. It's gonna define these things which are given in this figure here. So you need to look at this figure. Here's BF. Here's BW, what we saw before. So this is what we're trying to calculate, right? We're trying to determine BF. To determine this, we're going to need this BT. Okay, this BT is different than the one we saw here in the AS-min, right? AS-min, this is B small t. This, we're talking about something else here. This BT is the width, the length of the overhang. Okay, so this length of this overhang, this part, right? So there's these equations that give us formulas to determine this BT here. And then if we know BW, then we can determine BF. So here we have to go to this table. We have to know what all these things are. So BT is the overhang flange width. HF is the flange thickness. LN is the clear span of the beam. LW is the clear distance between two adjacent webs. So that's this distance, this clear distance here. So if I know all these information, I can use these equations to determine BT. BT is the smallest of these three things. And once I know it, then I can determine BF is just going to be 2 times BT plus BW, right? This is for the T-beam case. Okay, so you take the minimum of these three things. It'll give you a number. Once you know it, you take twice that plus BW gives you the BF, right? Because you look at this figure. Here, if I know BT, I know BW, I can determine BF. It's just 2 times BT plus BW. Okay, if you have an L-beam shape, then it's slightly different formulas. So if you have this type of shape like this, like at the edge of the building, then you would need to use these formulas which are shown here. Okay, so that's what I'm saying. Once the flange overhang width has been calculated, the effective flange width BF can be determined. For T-beams, it's this, and for L-beams, it's this. Okay, these are just the same thing. Okay, from Shalal's book. Okay, what he did is he just took those formulas for BT, like here, this one. This one gives us what? Ln over 5 is 0.2 ln, right? This one here, ln over 10 is 0.1 ln. So if I take 0.2 ln, okay, and I do, so if I do 2 times 0.2 ln plus BW, I'm going to end up with this formula, right? So it's the exact same thing that we just saw. Okay, so these are just the same thing in another format. So let's see an example on this because we had skipped that at the beginning of 4.1 example. So let's go to 4.1 examples, go back to the beginning of the handout, and we're going to do this example on calculating BF, because it will be more clear when we see an example. Okay, so this example that I'm going to do, it is solved in tutorial 4, part 1. I'll do this exact same example, but here I'm just going to do this part 1, part 2, and the tutorial, it continues to the rest of it. Okay, so let's start with this. So we have a simply supported T-beam, which spans 6 meters and has a cross section shown below. Okay, so this is like a section through that floor system, and we're trying to determine this BF. Okay, so if we remember, here's our T-beam. It's going to look something like this. Right, so here's our T-beam. Okay, so here it is. So this is what we're trying to determine. What is this BF? Okay, we're trying to determine what is this BF. To determine that, we said we have these things, which we called BT, like that, with capital BT. And here this is BW, and this thing is HF. And what we're trying to do is determine this thing, right? What is this thing here? Okay, so we have this floor system, and we're told it's a simply supported T-beam. So it's part of a thing like this. Okay, so this is the actual beam, and this section is what we're looking at here. Okay, so it's simply supported. Okay, so we're given all these different things. And here, let's say this is the clear span. Clear span. So this is this dimension. Ln equals 6 meters. Okay, so let's determine this. So BF this BF is equal to 2 times BT plus BW. Okay, so we have these formulas for BT. BT, it depends on the support conditions. So if you have simply supported, the first one here, and we take the minimum of these three things, the first one is just ln over 5, okay, or 0.2 ln. So I have 0.2 times 6,000. That gives me 1,200 millimeter. Okay, then the next one is 12 HF. So that's 12, and this is HF right here. 12 times 100. So that's also 1,200 millimeter. And then we have LW over 2. Okay, LW here I have this. So this is the first thing I'm going to need to determine. LW is the clear distance between the webs. Okay, so here I have LW1. And if I look at these things, these are all 300 millimeter. This is 300, 300, and 300. So LW1, if you do the thing, the 2.6 is center to center. So LW1 is the clear distance. So that's 2.3 meters. And then LW2 here also is 2.3 meters. Okay, and I'm trying to determine, I'm analyzing this T-beam here. And I'm trying to determine this BF. Okay, so I have LW1 on this side, which is 2.3. On the other side is 2.3. So they're the same. So I just add these, like half of the first one, half of the second one, and I will get this. Right, so it's, let's see here. So I have 2.3 over 2 plus 2.3 over 2, and then divide by 2. So it's just 2.3 over 2 in the end. And this is 1150 millimeters. So then I take the minimum of these three things. So I take the minimum of the first one, second one, third one, and I can see this is the one that controls. Right? So this controls. right here. This controls. So then I can say 2 times 1,100 plus BW, which is 300. So the total BF in this case is 2,600 millimeter. Okay, so that's the first example on how we determine this BF. Let's do another variation. So repeat the previous example. However, now consider that the T-beam is continuous. So instead of being simply supported like this, it's a continuous beam. Okay, what's going to be different? So this formula is the same. So BF is still 2 times BT plus BW, but the way we calculate BT is slightly different. Now it's the minimum of ln over 10. Okay, you have to go back to these notes. We said here that if it's a simply supported beam, we have ln over 5. For continuous beam, it's ln over 10. So we need to use ln over 10. So this is equal to 0.1 ln. That's 0.1 times 6,000. That's 600 millimeter. And then this one, these other ones should be the same. So 12 HF is 1,200 millimeter, and LW over 2 is the same. It's 1150 millimeter. So I compare these three. Again, I take the minimum. So in this case, the minimum, if I take the minimum, it's this one that controls. So here this controls for BT. So that means in this case, it's 2 times 600 plus 300. So in this case, I end up with 1,500 millimeter. Okay, so there's a couple of other variations that I'm going to do in the tutorial. So for these ones, see the tutorial. I change the span here, and you're going to see the BF changes again. And then I do an example for an L beam. Okay, so all these things are important, right? So it's, you have to consider these three things, and you need to look at the support conditions and these other things to determine the BF. So hopefully that example was clear for BF. Is there any question on this one? Okay, hopefully it's clear. So I will post that tutorial after today. So those that want to get, so you still have tutorial 3 to do, but if you want to get going on that, you can do that after today. All right, so why is LW 2.3? Okay, so LW, I have to look here. LW is the clear distance between two adjacent webs. If the beam has a different LW on the sides of the web, this okay, here I actually didn't follow this, what I wrote here. If the beam has different LW values on the sides of the web, the smaller value should be used when calculating BT and BL. Okay, I didn't catch that here. So here, we should actually just take the smaller of these two. Okay, so here we should take the smaller of these two. So let's say this was a different thing than here, then you take the smaller one. I'm not sure if I caught that in the tutorial as well, but that's the correct way. So this is just 2.3 meters. Okay, but in either case, you need to take this clear distance, okay, between the webs, right? There's one on this side and one on this side. I thought you take the average of the two, but it seems it's the smaller of the two. Okay, so I have to double check about this, but it's the clear distance here, Magd, between the beams, right? Between the webs of the beams. According to my notes, you take the smaller of the two. Here, they're both the same, right? 2.3 and 2.3. So that's why I took 2.3. Is that clear? You have to double check if you have two different values here, if you average them or you take the smaller. According to my notes, that's why I said don't always trust my notes. Okay, you need to check the code. But here I'm saying take the smaller of the two. So that probably is the correct thing. Not really clear. Okay, so all right, so we have to take the minimum of these three things. So ln over 5, hopefully everybody got that. It's the clear span here of the beam divided by 5. 12 HF is 12 times the thickness of the slab. For LW, it's the clear distance between the webs. There's one on this side on the left and there's one on the right. Okay, so you calculate this clear distance. How did I get it? It's 2.6. I know these beam widths are 300. So 2.6 minus 300 over 2 minus 300 over 2, I get the 2.3. Right, so you understood how I got the 2.3 at least. Okay, so that's how I got the 2.3. And then I did it on the other side and I got 2.3. So I had thought you take the average of the two, but according to my notes, you take the smaller of the two. Let's say this was 2.3 and 2.1, you just take the 2.1. Got it? Okay, but I'll double check this thing to be sure and I'll post on the forum if it's different than what I just said. Okay. All right, good. Okay, so this is this. All right. So maybe here just to be for the benefit of everybody, how did I get this? Right? L W is 2.6, which is the center to center between these things, minus 0.3 over 2 minus 0.3 over 2. That's how I got the 2.3 meters. Okay, so that's this one. If we continue with the handout here, the last part, there's some other requirements here. This is reinforcement in T-beam flanges. So when you have negative moment, okay, when you have negative moment, what's going to happen again? You're going to be in this situation. Tensions at the top, compressions at the bottom. So the steel, where is it going to be? It's going to be here in the top. Okay, steel is going to be here at the top. Steel in this situation. Steel is at top if M negative, right? So what this requirement is here is it tells you how to distribute that steel. Okay, how to distribute that steel. So in this situation, this is the compression face. The tension face, as I said, is at the top. Therefore, the tension reinforcement will be placed at the top of the cross section. In order to ensure an adequate beam to slab connection, a small portion of the required reinforcement should be distributed in the slab region to the two beam faces. So you do your analysis, right? You would analyze this like a rectangular beam, right? Here's the compression side. Then you would determine the amount of steel that you need to place here at the top. But what the code is saying is you don't just put all the steel right here, right? You don't just take all the steel and just put it in here, right? It's telling you place a certain amount of steel here on the outside, right? In these flanges. Okay, so how much do you put? It's right here. In order to ensure an adequate beam to slab connection, a small portion of the required reinforcement should be distributed in the slab region close to the beam web faces. This amount of reinforcement is given here. So you would need to calculate this stuff here. You'd need the B prime, which you get from here. And once you know that, you need to put this ASF, just as they're showing here, in these flange regions, right? You need to take the total amount of steel, place some of it into these flanges, and distribute it over a length here or a distance B prime. Okay, that's a fine detail in the code, but we need to be aware of it. Okay, this is only when you have negative moment. All right, so that's for this here. Okay, the last part is talking about the design procedure for T-beams. So these are just the design steps. It's actually exactly the same as what we saw for rectangular beams. So I'm not going to go through this here. So here are the steps. And in your tutorial, you continue here towards the end of the handout. There's this example, design example in tutorial 4. It will go through this design example and how you go through it. Okay, so that's for T-beam design. And in your assignment, the next one, not the one I posted, you'll also have a design example. So you'll need to check that tutorial on how you do this, or you can just self-study from this handout. It's filled out here. Okay, so that's for T-beams. That's for T-beams. Okay. Next, I want to go to double reinforced beams. Are there any questions on this, what we covered? All right, so let's go to double reinforced beams. So this topic is not going to be on the midterm, but we need to keep going with the course. So this is lecture 4.2, double reinforced beams. Okay, maybe just quickly about the midterm. Yeah, maybe it's a good point before we go to the next topic. Let's talk about the midterm. So the midterm is going to cover everything up to the end of last class. Okay, so what do you need to know? You need to know materials. Okay, but there's no theory. So there's not much there in materials. There's like a couple of examples we did. They might come, they might not come. Okay, so that's the first one. So don't like relook at the lecture theory again. You don't need to waste your time with that. But the examples that we did in the materials handout, you should be familiar with them. Okay. Next, we did loads. Okay, so how to determine dead load, how to draw V and M diagrams. Okay, so this you have to review. If you don't know how to draw basic shear moment diagrams, you need to know that. Okay, and we saw also how to check H-min, right, to avoid deflection checks. Okay, so that was in loads. The main things you need to know is how to determine dead load. So if I give you a simply supported beam or a cantilever beam with a certain defined cross section, how to determine the dead load for that, and then how to draw the shear and moment diagram with that information. Okay, we also saw these minimum thickness, how you choose the minimum thickness to avoid detailed deflection checks. That's all you need to know from loads. Okay, then we went to cracking moment. Okay, and then we did beam analysis. We saw how to do it by hand and how to do it using the CDH tables. We also saw in beam analysis how to do this bar spacing, Z factor, these checks, right? So these things you should know. And then we went to beam design. Okay, we saw these different things, like we saw direct, iterative, and then CDH tables, right? And then the other thing related to beam analysis that we saw is, and this is important for your midterm, non-rectangular. And we also saw over reinforced. Okay, so I'm definitely not going to ask you all this stuff here, okay? Because there's just an hour and a half in the midterm. So definitely study these non-rectangular beams, how you analyze them, how you analyze the over reinforced beam, and then how to do these things, bar spacing, Z factor, how to do a basic beam analysis. And then there's all these other stuff. Okay, so anything is fair game on the midterm, but those things that I highlighted are most likely gonna come. Emily, honestly, I haven't done the midterm yet, so I can't tell you, but you're looking at 3 to 4 questions for your midterm. Okay, 3 to 4, you can expect 3 to 4 questions. Okay, maybe next Tuesday I'll be able to talk more detail, but I haven't like written it yet. So this is it. So what I'll do is let's forget about T-beams. So T-beams, I'm going to keep it out. So everything up to the end of lecture 3.2. So up to end of lecture 3.2. And the way to study is just do the class examples. Start with that. Okay, next thing, do the tutorials. Next thing, do the assignments. If you do those three things and you fully understand them, then you will do well on the midterm. Okay, there's no surprises there. Is that good for everybody for the midterm? Okay, so just study up to the end of lecture 3.2. Just do the classics. Like if you have limited time, do class examples, tutorials, assignments, and you'll be ready for the midterm. Okay, so that's the way to study. All right, good. Okay, so let's now go to this tutorial, not tutorial, let's go to lecture 4.2. Okay, so this is talking about doubly reinforced beams. That's the next topic we have. So in practical design, it's often required to increase the factored moment resistance of a beam with tension-only steel. So we talked about this situation where we get into these over-reinforced beams that we need to avoid. But sometimes we're limited on the cross-sectional dimensions, right? We can't increase our cross-sectional dimensions. So, and we still have to resist that moment. So in that case, what's the solution? So one option, if we have the freedom, is we just increase the cross-sectional dimensions to make our beam under-reinforced, okay? But sometimes this is not possible because of architectural considerations. So in that case, you can provide an additional amount of reinforcement to resist the concrete compression stresses. It's going to help us to get out of that over-reinforced condition. So we're going to increase the amount of tension steel, but to compensate and keep the beam under-reinforced, we're going to provide an additional amount of reinforcement in the concrete compression zone, just like shown here. Again, we're going to call it AS prime, like this. Okay, this steel is called compression steel, and these beams, when we analyze them, accounting for the steel, we call them doubly reinforced beams. Okay, so that's the introduction. What's the primary benefit of using compression steel? It's exactly what I just mentioned. If we put too much steel and we get into these over-reinforced conditions, we said it's a brittle failure and the code doesn't allow us to go there anyways. Okay, it's brittle and also the code doesn't allow. So, but sometimes we need that amount of steel. So how do we solve that problem? We add these compression bars, and this can help us avoid this over-reinforced condition. So there's more details here, but that's basically the gist of it. Okay, there's other benefits of adding the compression steel. So even if the beam is ductile, when you add compression steel, it becomes even more ductile. Okay, so here, like this beam is ductile. It's failing in a ductile way. It still yields and still goes into here, and then it fails. But if you add compression steel, it'll become even more ductile. Okay, so it's one way to make the beam even more ductile. Another reason it's added is for this thing that we didn't see in detail in the course. It's something called long-term deflection, and it's related to creep, right? When you have this creep phenomena, we saw it increases the long-term deflections in our beams. When you add this compression steel, it will reduce those long-term deflections. And if you look at the code equation for deflection, which we didn't cover, it accounts for this compression steel. If you put compression steel, it will relax the deflection, okay? So it can reduce these long-term deflections. This is just a practical point. We said, and we'll see it later in the module 6, most of these beams in practice in buildings, they're continuous. So there's going to be some sections in here where if we want to account for this steel in both regions, tension and compression, we can use these principles that we just talked about, these double reinforced beam principles. Okay, but for us, we're going to focus on like a section, and we have an amount of steel and we're adding an extra amount here on the top. How do we determine the moment resistance? So let's start with the notation. So in addition to the previous notation found in singly reinforced beams, we have these additional notations. The first one is AS prime. Okay, so this is the steel here at the top. We're going to put this prime to distinguish it. If we find the steel ratio, so if we take AS prime divided by BD, that's rho prime. And then there's this distance, which is the distance from the compression phase to the centroid of this compression steel. We call it D prime. And then when we look at the forces, this is the force in the concrete and compression that we saw before. This is the force in the steel and tension that we saw before. What's new? We have this amount of force here, CR prime, which comes from these compression bars here. So we're going to see in our equations, we have this CR prime. Okay, so to determine the moment resistance of a beam with compression steel is determined in the same manner as the flexural resistance of a properly reinforced rectangular beam, except that now we include an additional steel force, which we call CR prime. So it's the same thing here, except we add this CR prime in our analysis. Okay, and we do the same assumptions. This beam is going to fail when this EC max reaches 0.0035. We're also going to assume that the steel here at the bottom in the tension side, it yields. Okay, so several situations can be possible for this compression steel. The first one is the top steel is in compression and it yields, right? So here we have a strain in this top steel. And here you can see it's above this neutral axis, so it's in compression. And let's say we do the calculation and we find it's yielding. So that's one situation. So the top steel is in compression plus it yields. That's one situation. Another situation is that the top steel can be in the compression zone, but the strain here is less than yielding. So that's another situation that can happen. Okay, and then there's an even more extreme situation. This neutral axis depth can be so high here, it can be above this top layer of steel, even above here. Okay, so it can be like this, right? If we have a very lightly reinforced beam, it can happen, right? The neutral axis can come like here, something like that. Okay, so in that case, this steel here is going to be actually in tension, right? Even if it's at the top, it will be in tension. So that's another situation that can happen. And again, you can have the yielding and not yielding situation. So it's very important now to be able to understand the strain diagram, because we need to know what situation we're in, because there's all these different combinations that can happen. So we remember this is the neutral axis depth. This is C, right? We remember this is 0.0035. What am I showing here? These are the strains, right? Here's the strain in the tension steel. And this is the strain in this top steel. Okay, so if I use these similar triangles, I can figure out what this strain is here. Okay, so I can try to figure out what this is just by using similar triangles. So, right, I have ES prime over 0.0035. And then here, what do I have? This distance from here to here is D prime. So if I have here C minus D prime, and then this here is C. So if I rearrange, I'll end up with this. So knowing these things, C and D prime, I can figure out what the strain in the steel is. And then I can know, is it in compression or is it in tension? And is it yielding or is it not yielding? Then I know which analysis I need to do. Okay, so we need to basically do assumptions and then check our assumptions. That's how it works for these double reinforced beams. So we'll start with the most simple one, assumption one. The bottom steel is in tension and it yields. And this is valid if CD is smaller than CD max. And then also we're going to assume the top steel is in compression and it yields. Okay, so and this will verify with these two things. If it's in compression, C is larger than this D prime value. And if it's yielding, then this ES prime that I just showed you how to calculate is going to be larger than epsilon Y. Okay, in that case, it's very easy, the analysis. So this CR prime is just going to be equal to phi S AS prime FY. And so this is the new force that we have in here. So it's the same force balance principle. The only thing is you add this CR prime, right? So this should be CR prime. This is CR, just to stick with the notation there. And this is TR. Okay, so this is the new thing that we're going to add, is this force here. And so we have it in here. And then to solve, we just do as before. We're going to solve for this A thing here, and we'll end up with this equation. And then we can determine C, and then we can check these assumptions. If it's valid, so we check the assumption like shown here, and we'll see that in the example. If the assumptions are valid, then we can find the force in the, so again, just to fix these to match what we have, this is CR. This is CR prime. This is TR. We can find all these things, and then to find MR, we just take moments about about the tension steel. We take the moments about the tension steel. We end up with this equation here, and that's how we get the moment resistance. Okay, but we need to check these assumptions, right? We need to check that the tension steel is yielding. We need to check this here. So if this passes, we continue. Then we check, is it the top steel, is it in compression? So we need to check C is larger than D prime. And is it yielding? We need to check this thing, ES prime larger than epsilon Y. If these things are not valid, we need to go to the next assumption, start again. Okay, the next assumption is, again, the bottom steel is in tension and it's yielding, but for the top steel, it's in compression, so C is larger than D prime, but it's not yielding. So epsilon S is less than epsilon Y. So then in that case, we need to be careful when we do this thing here, this CR prime, we need to be careful, right? Fs prime is not equal to Fy. So we need to do what we did for over-reinforced beams and determine a relationship for Fs prime based on Hooke's law. So we would do this here and use that here in this equation. And then we would solve for C by solving this quadratic. Okay, so we'd solve this quadratic. And then we would be able to determine C. And then just like the previous case, we'd have to check these assumptions, right? And we check these assumptions. If they pass, then it's good. If it doesn't pass, then we need to go to this assumption 3, where that top steel is actually in tension. I'm not going to cover this one, but that's also possible. So again, this would make more sense if we see an example. I'm talking for a long time. Let's look at these examples here. Let's go to 4.2 examples, double reinforced beams. Let's try to do the first example. Okay, so let's start here. 4.2 examples, double reinforced beams. Example 1, adding compression steel to an over-reinforced beam. So consider a beam which must be designed for MF of 827 kilonewton meter. We're told F prime C is 30 MPa, Fy is 400, and D is 499. Okay, so go to this one. 1 second. Give me a sec here. All right, so we're given this stuff here. We're going to set MF equals to MR as shown below. Okay, so let's start this example. So first thing, let's analyze this as if it is single reinforced. So it doesn't have any compression steel. So we have F prime C here of 30 MPa. If I go through the equations, you can do it later. You'll find alpha 1 is 0.805 and beta 1 is 0.895. Okay, the amount of steel that we're providing, so provided steel, bottom steel, is AS equals 10 times 30 M is 700 millimeters squared. That's 7,000 millimeters squared. Okay, let's just calculate rho S because I'll use it later. Rho S is 7,000 over B times D, or 199. So that's 2.81%. Okay, we'll come back to this amount of steel. Okay, for now, let's just start with this here, 7,000 millimeters squared. Okay, so let's assume that the steel is yielding. So let's assume that the steel is yielding. So in that case, this A value, if we have only this bottom steel, is just as we saw before. So that's 0.85 times AS 7,000 times FY, which is 400. And then I have alpha 1, which we have found is 0.805. Phi C is 0.65. F prime C is 30. And B is 500. If I do this, I get 303.2 millimeter. Okay, so 303.2 millimeter. Okay, so with that, I can find this MR. So MR is 0.85 times 7,000 times Fy, which is 400, times D, which is 499, minus A, which is 303 over 2. Okay, times 10 to the minus 6. I end up with 826.8 kilonewton meter. Okay, so here I can see I have 826 kilonewton meter. Okay, but there's the problem here. Okay, so what do I need to do here? Let me check this thing. So I need to check CD, right? Here we're assuming that we're yielding, right? We're assuming yielding. Here we're assuming yielding. So we always do this CD check. So C is just A over beta 1. So that's 303.2 over beta 1, which is 0.895. It gives me 339 millimeter. And then C over D is 339 over D, which is what? C over D. Okay, so let's do this here down here because we have it over here. So here we have C over D, which is 339 over D, which is 499. So if you do this, this is 0.67. Okay, if you remember, what's the CD max? It's 0.636, right? Or 0.64. So we can see we're above that. What does it mean here? That we have 0.67, and here we have the limit is 0.636. What does this mean? Anybody know? What does this mean? It means the beam is what? It doesn't yield, right? It's larger. I'm saying it's larger. So what does it mean? It means the beam is, what did we call it? We called it an over-reinforced beam, right? So beam is over-reinforced. Therefore, Fs is not equals to Fy, right? So steel does not yield, right? So this MR is actually not correct, right? MR is not equals to 826.8 is not correct. So if you wanted to determine the actual moment resistance of the beam, how would you do it? You would have to analyze it like an over-reinforced beam. But we said the code doesn't allow us to do that, right? So this is not the correct moment resistance. If I wanted to find it, I would need to go through these over-reinforced beam procedures. Okay, so therefore AS does not yield, and MR is in fact less than 827 kilonewton meter. Okay, so question, how can we avoid the over-reinforced condition? Okay, one option is we take this beam, instead of being 500 by whatever height it is, we change the dimensions, we make it larger. In that case, it might help us get a CD which is less than the CD max. Okay, that's one option. Another option, if these beam dimensions are fixed, is you add compression steel. Okay, so for this compression steel, I didn't mention it in the theory, but instead of just having rho smaller than rho balance, now we have this extra cushion when we add this compression steel. So now we just need to ensure that rho is smaller than rho balance plus rho prime. So we'll have ductile behavior if we ensure this. So for example, if we added 225 M bars, okay, so if you add 225 M bars at the top, okay, so you add 225 at the top. In that case, what's 225? It's 2 times 500 millimeters squared. Okay, that gives me 1000 millimeters squared. That corresponds to a rho prime is just AS prime over BD of 1000 over 500 times 499. It's equal to 0.4%. Okay, so in that case, let's look at these two situations. Without compression bars, our rho, we remember from here, from the top, it is 2.81%, right? And if I look up for F prime C of, how much is it? 30 MPa. If I look in table 2.1, we said at the top of the table, it gives you the rho balance. So rho balance here, it is equal to 2.63%. Okay, so if I close the table 2.1, but let me see here. Table 2.1. So if I go into table 2.1, I look up 30 MPa. Here's our rho balance, right? This rho balance is 2.63%. So our rho balance is 2.63%. So I can see here, everybody see why it didn't yield? I can see the rho that I used, 2.81%, is larger than rho balance. So this is why it was over-reinforced, right? And our CD check confirmed this. Now in this situation, what am I doing? I'm adding 225 M bars. So now with compression steel, with the compression steel, what do we have? We have a total rho here still of 2.81%, right? So here in this first situation, rho S is larger than rho balance. So this is over reinforced, right? In this situation now we have rho, which is still 2.81%, but it's smaller now than rho balance plus rho prime, right? If I look at rho balance, this is 2.63%, and rho prime, it is how much? It is is it 0.4%? Yes, 0.4%. So the total here is 3.04%, right? If you look at this here, so we compare these two numbers. This is the rho that I have in the beam. This is based on those 10 30 M's, right? Here we have 10 30 M's. It gave us 2.81%. And then rho balance for the F prime C is 2.63%. And then we said, let's add here in the top, let's add 225 right here and here. Let's add 225 M. That gives me this extra rho prime. So if I take rho balance plus rho prime, it's 0.4%. So if I compare these two numbers, I can see I'm going to be outside this over-reinforced condition. Everybody understood, right? So I want to add an amount of compression steel here to make sure I have this condition here, right? Rho is smaller than rho balance plus rho prime. So I'm going to add rho prime until I reach that situation. Okay, so that's how I figured out here to add 225 M bars to get past this 2.81%. Okay, this is just a note that the ductility requirement is more restrictive in the CSA standard, right? In the CSA, the new CSA standard, you don't need to just make sure that rho is smaller than this thing, right? You need to make sure it's smaller than 0.8 of this thing. So it's even more strict. But for the examples and this class, we're just gonna stick to this, right? So here, if I wanna just write it, the actual thing is rho has to be equal to smaller than 0.8 rho balance plus rho prime, right? This is the actual thing in the new code, but for us, we're just gonna stick to this one here. Okay, we're just going to use this one because that's what all the examples I have is based on. All right, I don't know if that was clear, but basically what I was trying to show here is that if I just have the 1030M, I'm going to be in the over-reinforced condition. Why? Because this CD is larger than CD max, or we said because rho is larger than rho balance of 2.63. So we need to somehow add an amount of steel here so we can get a cushion so that this 2.81 is smaller than rho balance plus rho prime. So we added this 225 M bars, which allowed us to get to 3.04. So now we were smaller and we ensure we're not in that over-reinforced situation. Okay, so that's that. I think this class has gotten a little heavy, so I'm going to stop here. So next class, we're going to continue this example. So now we figured out that we're putting in here 225M, right? And here we have 1030M. So the next step is how do you determine the moment resistance for this situation? Like we said, we're going to have to make an assumption and then solve according to that assumption. If it doesn't work, we need to go to the second assumption. So next class, we'll go through this example here, and then we will cover a second example, which is going to show another assumption. Okay, so those are the two examples we'll do next class. Are there any questions for today or about the midterm or anything? So I think everything is clear. So just to reiterate, you need to study up to the end of lecture 3.2, study using the examples, tutorials, and your assignments. Just a reminder, you have your assignment, which is due on Sunday. The midterm does not include T-beams, that's right. Okay, you have your assignment, which is due on Sunday, and then you also have your lab quiz 3. An announcement about the midterm in terms of what? So in terms of the content, I'll talk about it again next Tuesday, but the midterm, yes, I will announce when it is. Okay, so it's next Thursday during the class time for Catalina. If something's not clear, you can email me and I'll try to clarify it. Okay, if it becomes more clear, I'll make an announcement, but like you guys should know what to study. You just study those topics I mentioned. Expect 3 to 4 questions. Okay, but I will send an email, don't worry. Okay, so I'll try to send that during the weekend. Okay, so that's it for everybody, and we'll see you guys next week.